There's an often discussed belief among newer Go programmers that using pointers improves performance. While there are a lot of potential scenarios, let's look at one in particular. The example is quite simple. We have a struct with a bunch of fields in it that will take up a decent amount of memory. The theory is that if we create this struct and return a pointer, it will perform better than creating the struct and returning its value. The reasoning is that returning the value requires copying the struct values, but returning the pointer won't have to copy any memory, thus it will be faster. Let's give this theory a quick test. Oh, look, I'm finally using Go's built-in benchmarking in a video. The result of these benchmarks may be surprising to some. Returning a value is nearly 10 times faster than returning a pointer. How can this be? Before I dive into an explanation of why this is the case, let's do some more testing so we can see a bit more of what's happening. I threw this code together, running the two creation methods in loops and gathering CPU stats about each one. Looking at the pprof icicle graph of the value test, it actually seems as if nothing is happening at all, aside from the mysteriously named duff0, which sets all the memory in a new structure to 0. But things get really interesting when we look at the pointer executions. Suddenly, there's a lot going on, and it's all happening in the Go runtime. See, when you return a value from a function, both the struct in the function and the one returned are allocated on the stack, and the amount of stack space required is calculated at compile time. Sure, the values still need to be copied from one stack frame to another, but copying memory is quite fast on a modern computer. However, when you pass a pointer around, the runtime needs to find space on the heap to store the data. It has to do this at runtime, and this results in a lot of code within the runtime having to find space, possibly request more memory from the operating system, then properly set up everything to ensure the garbage collector can clean things up later. And this brings up something that wasn't obvious from the micro benchmarks. The garbage collector has had to run during the loop, and it seems to be taking up about 30% of the total execution time of the program. How much this actually impacts performance depends on whether there are free CPUs to do the work and other factors, thus it can be difficult to measure the total impact, but it shouldn't be ignored. The lesson then is don't use pointers on the assumption that they'll improve performance. Copying memory is very fast, thus your struct would have to be pretty massive for the data copy to be slower than the overhead of heap management.